Hey class, Adam Ward here. I want to talk to you today about the long-term storage, or what's going on with that mass that we don't get back in our solute tracer studies. And in particular, we're going to talk today about the channel water balance. And so before we go into this, I think it's easy to use an analogy and think about what happens in our bank account. So let's think in the month of October, for example. Perhaps the balance in my bank starts at $500 at the beginning of the month, and at the end of the month, it's $625. Now, what we learned from that is I had a net gain of $125. And it's tempting to think about a bank account at this level because it's very simple, right? Either the balance went up or it went down, and I can tell you exactly how much. But the reality of a bank statement reveals it's much more complicated than that. So what actually might have happened over the course of the month, perhaps I spent $50 on groceries, somebody Venmoed me $25 to pay me back, I had a $1,000 paycheck come in, then I spent money on rent and registered for a conference, let's say. And so what we find is that through the month, my balance did not just go up by $125. In fact, it's substantially more complicated than this. In total, there was $1,025 that came in, $900 that went out, and the net change between those two is that $125. So all transactions taken together gets us to $125. Now this idea, this is exactly what we want to do for streams. Rather than simply keep track of the net change, which would be a stream that is either gaining or losing, we want to keep track of all of the inflows and all of the outflows of water along a segment. So when we first talked about streams, so this was perhaps in an undergraduate class, we had this naive conceptual model of streams where we would compare the discharge at the upstream and downstream end. And if there's more flow downstream, we called it gaining. If there's more flow upstream, we called it losing. And by taking this view of a stream, what you're seeing is essentially the simplest possible assessment. This is like the orange pen on the previous slide. That's like saying what was the net change over the course of the month in your bank account or over the course of the stream in discharge. So instead, or there was one other sort of conceptualization which was actually the most accurate. People who would think of a stream as a flow-through system. And this was typically streams cutting across a mountain front where they were envisioned to gain from the steeper upslope side and lose to the down valley side. But that's actually a more accurate picture because it at least has gains and losing happening at the same time. So the model that we're going to follow comes from Rob Payne and others in a 2009 publication. This is a figure 1 borrowed out of that image. And the idea here is that the region that they've dashed, and which I've covered in blue, is a study reach. And so we've got a tracer released at the upstream end and observed at the downstream end. And what Payne did was go through and conceptually tally up what are all the gains and losses we might have. So flow path E could represent tracer that you lose because it goes to some deep regional groundwater system. This could be 10,000 years or more in its transit time. Flow paths labeled D in this image might represent what we call underflow or down valley flow in the subsurface. So it will come back to the stream, but just not within the study reach or not within the study reach that we're seeing. So if you can see flow path D, those both bypass the downstream end of the reach. So that mass appears lost because it doesn't go through the stream. It flows underneath your sensor. On flow path C, this is the window of detection problem that we talked about early. That flow path will come back within the study reach, but it's simply not coming back fast enough for you to detect that mass. So that mass shows up as lost. There are also gains of water that we might experience along the way. So gains from the catchment, flow path A. Gains that were underflow that began upstream of your injection but returns within your study reach. And of course, hypereic exchange or transient storage, flow path F, is both a loss and a gain that's happening simultaneously. And so what the advance was of Payne et al. Was this idea that we could actually keep track of this. We may not be able to differentiate these individual flow paths, but certainly we can keep track at least of the gains and the losses. We can do better than just the net change. And so that's what we're going to set out to do. All right, let's actually quantify the sum of the gains, gross gains, and the sum of the losses, which we call gross losses. And those can be related to that initial net gaining or net losing assessment. So let's look at how this actually plays out. First, let's talk field methods. So the setup that is used by Payne et al. Is the same as the setup that you've been working with through the course of the semester, where we pick out a study reach, we have a downstream observation site, DS, and an upstream site, US. And at each of those reaches, we estimate a mixing length, and we're going to conduct an injection at the one mixing length upstream. So the first thing we do is an injection at the downstream end, and you can see I've drawn sort of a red breakthrough curve in the bottom right set of axes to represent that. Then we go to the upstream end of our, we do that so that we can get the flow at the downstream end via dilution gauging. So that red injection, its whole purpose is to get flow at the downstream end of the study reach. You absolutely could instead go out with a velocity meter and make measurements that way, or you could set that up to be co-located with a stream gauge. Then you would walk to the upstream end of your study reach, where I'm showing the second injection happen in purple. We can use that to get discharge at the upstream end of our study reach. And then if we've left our downstream logger in place, we can actually watch that upstream injection when it passes by the downstream logger. And that's what we're going to use to infer things about transport and storage within the study reach. So Payne's design would have 3 breakthrough curves in total for each study reach, and that's exactly the same as what we've been doing in this class. Okay, so let's clear out some of the details here and actually talk through some calculations. First, a simple one. If you know the discharge at the downstream and upstream end, you can decide the Q net. Is your system net gaining or net losing? One of the other essential bits that Payne would have us collect is to characterize the mass recovery at the downstream end. Now, in other words, we know how much mass we released in the upstream injection, the purple injection. How much of that did we actually see come by the downstream end? So that mass recovery is asking how much mass from injection 2 upstream passed by the downstream location. And it is explicitly about the area underneath this bottom right breakthrough curve that I've just hatched in yellow. So that's how much of your upstream signal you could see at the downstream location. And finally, if you know how much mass you lost, or that you recovered, you could calculate how much mass you've lost. So the difference between what you released and what you found back is your mass loss. That mass loss, the amount of your tracer that did not remain in the stream system, the amount that you can't account for where it went, that's the critical piece of information here, because that's going to let us start to get at the gross losses from the channel, and then we can back our way into the gross gains. So on the these 3 calculations, the net change in discharge, mass recovery, and mass loss, we need all 3 of those, and we will have to have known the discharge at the up and downstream ends before we proceed any farther. So with those in hand, let's see what Payne would have us do. And so in the manuscript associated with this lecture, we end up analyzing 2 end members, one that's called gain before loss and one that's loss before gain. And I want to go through these calculations and show you why we have end members and not just simply a number, but we end up with a range. So the first case we'll look at, the left-hand side of the screen, is gain before loss. So in other words, we want to envision a system where we inject our tracer in orange. We first have dilution of that signal by all the gains, and then we have all of the losses. In other words, we dilute before we lose. So if you want to remove mass from the system, if you dilute it first, it takes more outflow to take that mass out of the stream. So gain before loss is the case that will get us the maximum volume of water in our gross gains and gross losses. to calculate this maximum gross loss is your mass loss in the numerator, and in the denominator it is the integral of the upstream concentration at the downstream logger. That's the breakthrough curve I had hatched in yellow on the previous slide. And with that Q loss calculated, you can use the water balance then to get at the gross gains. So if I know the net change in discharge and the gross loss, I can back out of that Q gain max, or the maximum gains. Now the second end member that we're going to look at has things in the opposite order. So we assume that we inject our tracer there in orange, we lose all of the high concentration water, and then the dilution happens. And the consequence of the assumption of gains and losses in that order is this is the least possible volume of water you could remove to lose the mass, to account for your mass loss. Right? And so you can go through and calculate Q loss min. It's very similar, but you'll notice in the denominator there, it's the upstream slug at the upstream end of the study reach. So that's the purple slug at the upstream end, the one that we used for dilution gauging at the upstream end. So upstream injection at upstream logger. And then the Q gain min is the same calculation. What these ultimately do is use tracer mass balance to get at the gross losses, and then they use a water mass balance to get at the gross gains. Again, the reason that we have these two end members is we don't actually know the order in which these happen. So order of operations matters here. Do you dilute before you remove the tracer, or do you remove the tracer and then dilute what remains? That order of operations matters, and since we can't know it, the best that we can do is bound it. So we'll pick either, what we know is that the gross losses must be somewhere between the minimum and the maximum that we calculate. Similarly, the gains must be between the minimum and the maximum that we calculate. And so using this strategy lets us do something with that lost mass. For maybe 25 years of solute tracer studies, we focused on what we got back, or the short-term storage. And what was really a breakthrough in this paper was to say, look, there is knowledge to be gained, there is science to be done by understanding losses of mass from our system. So no longer is our mass simply lost and we don't think about it. We recognize that the loss of tracer mass actually tells us something about the system and the flows of water coming and going. So I strongly encourage you to take a look through the Payne paper. It is very detailed in terms of its technical treatment, and I hope that the slides here help you unpack why this works and what these two end members, the max and min cases, represent and how they behave. Thanks for sticking with me all, and in the next video we'll look at how to aggregate these kind of changes along a network to think about the turnover of water between a stream and its valley. Thanks.